Hello everyone and welcome from our side. We are Gioele Simonte and Giacomo Sernia, vascular surgeons working in Perugia, Italy. We have the privilege of guiding you through this video course focusing on the inside of the shelf thoracoabdominal endograft by Artivion.
The first will be done by Gioele, who exploit at their prime the inner branch technologies with pros and cons. The second chapter is on my own, and it is a comprehensive product detail on this device, with in the second part a planning and sizing example. The first chapter is again on Gioele, and it is an amazing mock deployment performed in our hybrid OR in Perugia, with a sequential step-by-step deployment of E-nside endograft, with also inner branch cannulation. I hope you will enjoy all this video session, and now please, Gioele, the stage is yours.
Thank you, Giacomo. So in this first chapter, we are going to analyze the benefits provided by the inner branch technology and the rationale behind the idea of developing an off-the-shelf graft based on this solution. Well, there's no doubt that an endovascular approach to thoracoabdominal aortic aneurysms represents nowadays a safe and effective alternative to open repair, showing in some cases even better results in short and mid-term. Long-term bridge stent patency still remains an issue. And the strong evidence regarding the ideal endograft configuration and the ideal bridging component to be used inside visceral vessels is still missing. And this uncertainty, inner branches may represent something in between fenestrations and other branches, offering advantages from both worlds. Guaranteeing stable anchoring for bridging components, this design aims to improve immediate technical success, but also to provide an effective target vessel vascularization for the long run. One of the features most appreciated with IBVAR grafts is their versatility and the capability of treating with the same kind of device different aortic pathologies. We can easily perform extensive aortic repairs as in type 2 thoracoabdominal aneurysms like you see in the picture, or treat difficult, challenging previous endovascular failures, as in this case in which we faced a proximal type 1 endoleak in a patient with bilateral renal stenting, so with high risk of dealing with these renal arteries, and effectively performed the repair using this custom-made 400-grade inner branch graft, really without encountering any particular difficulty. Inner branches offer perhaps the most significant advantages when dealing with narrow anatomies, allowing the effective endograft usage even in case of very narrow lumina. In this case, we had an old, frail patient with a pararenal aneurysm and a quite challenging anatomy because both tortuous and narrow at the origin of the renals. And he was treated again with this custom-made inner branched graft, and this probably represented the only possible endovascular alternative, as according to our opinion, neither a fenestrated or an outer branched graft would have been viable with this particular anatomy. So to better understand the advantages, we can compare inner branches with their historical competitors, starting from fenestrated graft, which have been for years our preferred treatment options in patients with para and juxtarenal aneurysms. The lack of proximal stent support may determine situation like this one, in which we had a tight stenosis at the superior mesenteric artery bridging component proximal end, asymptomatic and identified at a CT scan performed a couple of days after the procedure, so we had to perform an early reintervention, re-expanding and reflaring the bridging component. And again, having only a ring for proximal stent support makes the final stent position in some cases quite unpredictable, and it is possible to end having a stent conflict like in this case. Stent disconnection may also occur during follow-up, a complication less likely to happen in case of long and stable docking zone, especially proximally of course, as we have in case of branched endograft, whether internal or external. So inner branches provide a platform guaranteeing a stable anchoring and a predictable final position for covered stent into our target visceral vessels, working also in case of narrow aortic lumen. And this makes the technology useful not just for the treatment of extensive aortic disease, as said, but also in case of more localized pathology, as in case of para and juxtarenal aneurysm or for proximal type 1 endoleak correction after EVAR. We have here another example of a patient with graft migration and recurrent aneurysm after EVAR, treated again with a custom-made 4 inner branched graft with a beautiful final result. These images, in my mind, are quite self-explanatory of the IBVAR concept. You find in this post-operative CT scan highlighted in blue the aortic lumen filled by the main graft, and in yellow we have the free gap outside of the graft. The IBVAR concept generally relies on leaving enough space outside of the graft to allow for a safe navigation and cannulation towards the target visceral vessel. And you see also in this image how there is generally sufficient space outside of the graft to easily catheterize the target visceral vessel, and this makes the whole procedure much more forgiving both in terms of planning and in terms of deployment. Fenestrated grafts, on the other hand, are generally conceived to minimize the gap in between the aortic wall and the endograft surface to enhance proximal sealing. And you see on the left side of the slide how the main body of the graft is filling the whole aortic lumen at the origin of the target visceral vessels. Inner branches provide some advantages even against standard outer branched graft, the most important of which is the prevention of compression and meshing of branches and bridging component against the aortic wall. In this case, for example, we treated in emergency setting a patient with a juxtarenal aneurysm with an off-the-shelf 4 outer branched graft, and you see on the axial images how again in case of narrow aortic lumen it is possible to have this compression in between the main body of the graft and the aortic intima. And the exit angle is generally much more gentle, reducing the risk for kinks and the need for bare metal stent relining. So with all these premises, Artivion decided to develop an off-the-shelf graft based on the inner branch technology, specifically designed to treat a broad spectrum of anatomies and providing furthermore the advantage of having precannulated catheter for each inner branch. And we are going to dive deep into details about this graft, planning and sizing, and some case examples in the next chapters.
In the second chapter, we are going to explore why E-nside and the rationale behind this new endograft, and in particular all the product details in terms of structural feature of the E-nside. In the second part, we're trying to explore also the characteristic of this endograft, but in particular the planning and sizing in a real example. The first question to answer is why E-nside? All this project arises from a strong and consistent experience obtained from the complex aortic repair treated with custom-made extra design provided by Artivion. The main indication was for thoracoabdominal aneurysm repair, but thanks to its own feature, this graft is intended to use for a consistent and effective approach in a large variety of anatomy, including recurrent thoracoabdominal aortic aneurysm after surgical or endovascular repair. The system provides an off-the-shelf solution for elective and emergency case, representing the first and only available in the market all 4 branches precannulated inner branch device. Before speaking about planning and sizing technique, in my mind, it's mandatory to have a quick review on product structure details, to better understand what we are talking about. The skeleton graft is made of a nitinol steel sutured with a polyester fabric. All the markers are clearly visible under fluoroscopy thanks to gold and platinum manufacture. The 5 proximal tubular markers allow a good parallax adjustment after deployment, while the E marker provide 2 critical functions. The first is to display the maximum and minimum overlapping with the thoracic component. The second to provide the rotational orientation of the stent graft itself. In the distal portion, the endograft presents a totally different marker called E marker, positioned 35 mm distal to the lowest inner branch, marking the distal overlapping with a bifurcated of tubular component, of course if needed. The middle portion of the endograft is the core of the system, harboring 4 inner branches, each one with 3 tubular markers scoring the outlet and 1 ring marker for the correct bridging stent positioning and the deployment. Artivion provides us 4 different codes, 2 different proximal diameter and 2 distal diameter, with a fixed 24 mm middle portion. All 4 inner tunnels present with an enlarged oval-shaped outlet, increasing the chance to the target visceral vessel catheterization. In terms of visceral vessel catheterization feasibility, according to this well-known study, the endograft reached a 97% of cases, in particular thanks to this dedicated inner branch outlet configuration. Artivion addressed a particular attention to its branch design to improve bridging stent patency and reduce stent-related complications. This is the purpose of the asymmetrical compression spring, a stent that increases dramatically the resistance to the longitudinal compression. Moreover, the presence of a stability seam enhances the longitudinal stability and the navigability through the inner branch itself. Finally, the MRS migration reduction system, in other words, a suture 0.1 mm thick in the middle of each branch that aims to maximize fixation and reduce bridging stent disconnection during the follow-up. In terms of indication and applicability, we need an adequate iliac and femoral access compatible with 8.5 mm outer diameter delivery system. We need also a length of at least 30 mm in proximal overlapping with the thoracic stent graft and a good distal landing zone of 30 mm. The high difference between the outlet of the inner branches of the graft and the ostium of each target vessel must be in between 10 and 50 mm, and all the target vessels must be suitable for an antegrade cannulation. These are all the planning and sizing documents provided by Artivion for E-nside endograft that helps you during all the planning session. The first one is the sizing sheet that includes all relevant measurements for a case planning, including measurements for thoracic stent graft that respecting IFU is needed. All the planning process consider as the 0 point the ostium of the celiac trunk. From this point we must calculate the distance with left subclavian artery for the thoracic measurement. The aortic length L2 is the distance between the lowest renal artery to the native bifurcation. And finally, L3 and L4 the length of right and left common iliac artery, of course if a bifurcated component if needed to complete the endograft implantation. The visceral vessel distance is definitely the most important point to deal with, because considering the CT ostium, the 0 point, we calculate the distance from this point to superior mesenteric artery, to right renal artery and to left renal artery, and we can report all these 3 measurements in the dedicated form. Afterward, we must evaluate the diameter of the proximal visceral vessel and distal visceral vessel, of course, before any kind of bifurcation. In an axial projection, to complete our measurement, we calculate the takeoff angle of each target vessels in this dedicated section. The question now is how we can verify the feasibility of each case after all this measurement. This is the graft in which we must allocate each visual vessel ostia with a dot, considering the celiac trunk, the 0 point, and the takeoff angle on an axial line. We can easily apply the feasibility mask by aligning it with the 0 point. You can clearly see that the cones below of each inner branches don't fit the model in this case. But with a simple movement of 10 mm above and 10 degrees clockwise of the feasibility mask, we could consider the model applicable for this patient. It's essential to stay as close as possible to the vessel ostium to reduce proximal aortic coverage and bridging stent length. We are happy with our project and finalize the process choosing the proximal and distal endograft diameter. Don't forget, as said before, to assess the vascular accesses, both femoral and iliac, to exclude any possible related complication.
So in the third chapter, we are going to see in detail how to actually implant an inside graft, describing each procedural passage. For this purpose, we recorded a mock deployment in a transparent silicone model to better understand the peculiar device features along with how the preloaded mechanism actually operates. The inside graft comes with the classic Yotec delivery system design with the addition of the preloaded control mechanism at its proximal end. An aortic sketch indicates here the correspondence for each preloaded catheters with the proper inner branch. The handle is a squeeze to release, as with other Artivion products, with a tactile marker helping for rotation orientation. Implanting sequence begins with graft advancement up to the intended deployment level, while correct graft rotation mostly relies on the position of the two ventral E markers located at the cranial end of the graft, which in anterior-posterior projection should remain in the aortic center line. After the device has been properly positioned, the handle can be switched to drive mode and the device initially deployed using the orange lever. After first couple of stents have been sheathed, the markers can be repositioned at the center of the projection, reorienting once again the graft, while the high lever should be carefully assessed at the very beginning, matching the inner branch outlet markers with the corresponding target vessel origin, the latter highlighted after shooting an angio or using fusion technology where available. When final graft position is confirmed, deployment sequence can proceed, and it can be seen through the transparent model how once inner branch outlet are unsheathed, the preloaded microcatheters passing from distal outside to proximal inside each inner branch become visible. When the graft is fully released, the proximal capture tip can be deployed, and that's finally the moment where the preloaded mechanism becomes paramount. The operator should now remove the safety wire in one of the 4 precannulated catheters, flush the line with heparin, and advance an 018 guide wire into its channel. This guide wire should be 4 meters long and non-hydrophilic to reduce friction during advancement. Its movement can be seen under fluoroscopy until it reaches the proximal end of the endograft, where a snare coming from an upper axis, whether axillary or brachial, reaches the wire, captures its tip, establishing a femoral brachial or a femoral axillary through and through. Over this through and through then, a long introducer sheet, large enough to accommodate the bridging components to be used, is advanced until it exits from the graft, passing across the proper inner branch. And with the introducer sheet in this convenient position, a diagnostic catheter is advanced double puncturing the hemostatic valve of the introducer sheath, maintaining the true and true, and this diagnostic catheter is then used to cannulate the target visceral vessel along with an hydrophilic guide wire. Once cannulation is achieved, the guide wire can be exchanged with a more supportive one, and the bridging component finally advanced in a proper position, providing a long enough proximal and distal sealing zone. Then the bridging component is released and the first vessel revascularized. Each maneuver should be then repeated for the remaining visceral vessels, and we have here some images from an actual real procedure performed in our hybrid operating room. You see here establishing for the first time of the true and true, advancing the long introducer sheath and bridging the first visceral vessel, which in this case was the superior mesenteric artery. Again, the true and true is established, the long introducer sheath advanced until outside of the graft, target visceral vessel catheterized and bridged with a covered stent. Third vessel in this case was the right renal artery. The sequence is not really that important. It can be decided by the operator at the moment. You see here advancement of the 018 guide wire, establishing again the true and true, advancement of the introducer sheath, and at the end of the covered stent, bridging the third gap. That's the angio control. And last but not least, we have the celiac trunk. So safety wire removed again, true and true established. You can see here the advancement of the introducer sheath clearly outside of the graft in this projection, and deployment of the final bridging component. After each visceral vessel has been revascularized, the handle can be switched to neutral mode, the tip retracted, and after switching again the handle in park mode, the delivery system can be removed from the femoral artery. Distal segments can be added if needed, and finally the operator can enjoy a beautiful angiographic result like we did in this case.